Okay, cool. Thanks very much. So can everyone hear me okay in the back? Is this like a good level? Yeah, okay, awesome. So I'm going to talk about machine learning startups, which I've been doing for about a decade now. Quick look at my background just on a timeline. So I double majored in computer science and finance. I went to Virginia Tech. I started a thing called DNFM, which was a hedge fund. I worked at another hedge fund called O'Higgins Asset Management. I started doing all that in the early 2000s. So my first job out of school was applying machine learning for fully automated machine learning-driven trading systems. In 2007, I decided to switch and go into tech, moved out to the Silicon Valley, worked at Google for 2 years on a project called Borg. If any of you know Mesos, anyone know Mesos? This is also what Spark is built on. Mesos is built based on Borg. And so is this shirt, which is my friend's company called Mesosphere. So Flightcaster is the first startup I started after spending 2 years building distributed systems at Google. Flightcaster was predicting flight delays using machine learning. Cool. So then I started doing a PhD at Berkeley in 2010. It was a very theoretical, math-focused machine learning PhD. And then I immediately stopped doing it a year later because I switched from being like a chief scientist to a CEO, which was a terrible idea. I'm not sure why I did that. Then I started DCVC, which is the largest AI-focused venture capital fund in the world now, with about $1 billion in capital under management. And I started Prismatic, my second machine learning startup, after we sold Flightcaster. So I'll be talking more about that today. And then now in 2016, I just had sold Prismatic to LinkedIn in December. And then I started Raptor, Tower Street, and CAI, which I'll be talking about later in the talk. So this is kind of my life story here. So first, some lessons learned on machine learning-driven startups. So first is turn hard problems into easy ones. Don't try to solve hard problems. It's a bad idea. That ultimately, you really have to focus on casting the research problem correctly. And most of the challenges in really tackling these things come with setting up the problem correctly. And I think a good example of this is going to come when we talk about Tower Street for cyber insurance in a little bit. And then you got to be creative about bootstrapping training data. A lot of times when you're doing this as a startup, it's not like you're going to join Google and you have a shitload of click data and everything is great. Oftentimes you have not enough data for what you're trying to get done. Other lessons are that, ultimately with machine learning, you're really trying to capture sort of joint distributions, right? There's many ways to do that. You can do it with different types of models. You can do it with featureizing in different ways. You can do it with building training data in different ways. And I think, to really do this stuff effectively, you've got to understand it deeply, and you've got to know which of these weapons you want to bring to bear at what time. You can't just throw neural nets at shit and expect it's going to work. And then training data and features are greater than models, I think. Ultimately, there's a lot of different models you can throw at different problems, and really what matters a lot more than that is whether or not you have data that gives you the statistical power to actually do something. And then a model is not a product. Nobody cares about your ideas. So what do I mean by this? This is the proverbial hammer looking for a nail. So oftentimes, I think when people try to do these AI-driven startups, myself included with my first couple ones, we'll focus on things that we think are really interesting, but then nobody else in the world thinks it's interesting. And I think that's a huge problem. So I think you want to search for nails and then engineer your hammer to fit the nails instead of the other way around. Just look at the poor nail, right? This guy's not doing so well. Okay, so Flightcaster. This is about predicting the real-time state of the global air traffic network. What's the prediction problem? It's pretty simple. You have a flight departing at time t. You have a bunch of data before that. You want to know the likelihood that it takes off at time t or time t+1, et cetera. So featureizing the data. Basically, we have carrier data. That means data from the airlines themselves. You have FAA data that in the US, that's the Federal Aviation Administration. And then you have weather data. And you have a nightly reset, which provides a natural cadence for rolling up feature vectors, right? You don't have a really nasty spillover problem where dependencies go on and on and on for many days because planes are grounded at night. So that's pretty great. And every aircraft has a unique tail number. That's this thing right here. So you can join on those. So you have this kind of fuzzy K-way join. You have tail numbers, you have time, you have location, and you have these different data sets, and you have to join them and try to figure out how to map this plane through time during the day, right? That's what you're trying to do. And then at each given time, you're trying to make a prediction about what's going to happen to these subsequent flights that are supposed to take off, right? Because now you know what's happening with the airplane in an earlier moment in time during the day. So 6 hours before the flight takes off, I have some sense of where the aircraft is, what the airports are that it's going to fly through, what the weather looks like there, if there's any FAA holds there, et cetera, and I can kind of try to featurize all that and predict what's going to happen with this aircraft. And an interesting note about this is a case where you kind of have fuzzy training data because you don't actually have 100% accuracy on these joins, because the data is actually crap that comes from the carriers itself. They're actually manually inputting this stuff and so on. So these tail numbers are not 100% accurate. The times can be wrong. The locations can be wrong. And so you kind of have these noisy labels, which is kind of making the problem a little bit more interesting. So as I mentioned, some interesting things you want to look at for featurizing it are positions in the past, weather and status. You can get groundings. For example, if there's like a snowstorm, the FAA will just ground all flights at that airport for several hours. So that's a feature you obviously want to use. And then time, it becomes really interesting because you have many times before the flight takes off, and then you have times that you're trying to predict from the time that it's supposed to take off. And so you have many different interesting ways to do feature crosses by looking at time. Models. So I think this is an interesting case for what I talked about earlier. We tried trees, we tried a bunch of different linear models, and trees were kind of working a little bit better initially, many different kinds of tree-based models. But ultimately, once we figured out more ways to featurize time and other dependencies in the network, then they became basically the same, and it was a wash. And there was like 6 different models that had more or less identical performance. It didn't really matter what we used in production. Tools of deployment. So this was back in 2008, and we were one of the first startups in the world using Clojure in production at large scale. We were doing it on top of Hadoop. We wrapped everything in a really simple API. It was pretty nice to use, and I think this was really validating my theory that I had had for years that functional programming would be awesome for these kind of data pipelines and machine learning problems. But I think the production model we had really sucked. I'm going to talk more about this in a section. I would actually write the models to JSON. We had a team that had already started building the app before I started building all the back-end tech, and that was being done in Rails. So they were reading these JSON objects in, and we had to sort of write this little hacked framework for reading a JSON model and making predictions based on the JSON model, and then storing data in the SQL database, and then I would have to snarf it back out as my sort of as my data for training on an ongoing basis. So that kind of sucked. The other thing I learned was the log-based debugging paradigm really sucks. So if you're deploying stuff into Hadoop and then you try to debug all these ETL and feature engineering issues, it's really horrible, right? The feedback loop is really slow. It's really crappy. And basically, the other side of the coin, though, is that if you just do this at trivial scale on a really small sample on one machine, oftentimes you don't really find anything that interesting either. So I think a big learning there for me was that you need to find stuff in between where you can run it on a meaningful amount of data, but you're not putting it into a full-blown Hadoop job and finding stuff in logs, right? Dirty data, I mentioned that. There was manually entered data. That really sucks. That means that you have to think about noisy labels, and you have to think about learning in a way that's robust to noisy labels. It was early days of Clojure and Hadoop. I literally found 3 or 4 actual language bugs in a Hadoop mapper, which is really frustrating, when a mapper breaks and you're finding a language bug inside a mapper log. That's awful. And then I think, again, like deploying the JSON models rather than services was kind of bad. Again, model selection mattered less than featurizing. I think that's a thing you'll see throughout this presentation that comes up again and again. And there's many ways to capture dependencies, right? It's like, I always try to think about machine learning from a perspective of information theory or statistics. And it's like you're trying to capture joint distributions and information about that. How much gain does it give you against the target? And basically, when you think about it that way, then you're going to have a broader perspective, and you're going to think about what information do I have in my training data, what ways can I exploit that information through featurizing it, and then what's the right kind of model to apply to that. And then you're always going to be kind of picking the right tool for the right job instead of just trying to try a bunch of models and see what works best. Because you might not even be able to learn the thing you're trying to learn, right? The data might be too sparse in part of the input space where a very important type of prediction is happening, and then there's nothing you can even do, right, unless you can figure out a way to bootstrap better training data. I also learned that these intuitions of the domain expert can be useful, but they can also be misleading. Sometimes they think they have very, very precise idea of what's going to work, and actually engineering features based on their insight is probably not a good idea, but letting them identify data sources for you is really interesting because they're going to help you find really good sources of data. After that, though, I recommend taking a really scientific approach to exploring the feature space and just getting a good feedback loop going, building good infrastructure to explore a lot of stuff really fast. We also found this issue with the Hadoop thing, like I mentioned, right? I really got to thinking a lot more at this point about building computational graphs, where you have the idea of a higher order function wrapping every node in the graph and logging structured data to a different kind of store where you can then go and get debug information from it. And also the idea that you could compose that graph to run in a single thread, in multiple threads, and multiple processes on multiple machines and gradually scale it up. And I think that ended up being hugely inspirational to us in what we did with Prismatic. There's actually a GitHub repo called Plumbing, if anyone wants to go look at this. This contains all of the cool open source closure stuff that we built in Prismatic, which is largely inspired by a lot of these kind of lessons learned from flight casting. And then, like I said, production wasn't great. I think ultimately you want these little microservices and stick your models behind those, and then you have your back-end team that's doing all the heavy lifting, machine learning, distributed systems, and so on to just put up the models behind microservices, and then you have your full-stack product team that's just calling those. I think that's the right production model for deploying machine learning services. Like I said, a model is not a product. What we did with Flightcaster at the end of the day is we had this distribution of when you were likely to leave at different times away from departure, right? So it's like a discretized probability distribution. We just showed it as a bar graph, and nobody can figure out what the hell you're supposed to do with that, right? So you got to turn this into a recommendation or something. It's like, tell me if I should rebook my flight, right? Recommend a better flight for me to take. It's not useful for me if I know that it's 65% likely that my flight is going to be delayed by 45 minutes or more. If I'm a normal human being, what the fuck am I going to do with that, right? Nothing. Because it's just there's not actionable, right? I barely even understand what to do with that, let alone a person who doesn't understand what a probability distribution even is. Okay, so Prismatic, this was about personalized ranking of people, content, topics, etc. Basically, personally ranked news feed akin to Facebook, but for content based on your interests. And then lots of recommendations of these kind of different factors that we called interests, like people or topics or entities or so on that you could follow that would come into your news feed. So basically, given a big index of content, display the stuff that maximizes user engagement. I think everyone's probably super familiar with this problem, so I'm going to go through this part really fast. The main thing is, like, you can't, ultimately you want to maximize long-term engagement, right? And these things like, number of days per month and so on, but that's not really a suitable feedback loop to learn off of. So instead, what you do is you try to come up with heuristic proxies for that based on short-term engagements, like likes, shares, all that kind of stuff. So we got our content through focus crawling on Twitter, Facebook, and on the web. It's a little bit different than just normal web crawling because you're kind of trying to get like the maximum amount of interesting, focused content, and you don't really want to get all this non-feed content out there on the web. You don't want to go everywhere. You're really risky to get a ton of spam in there because it makes the spam problem even worse, and it's already really hard in this domain. And then you have a ton of spam content and deduping problems. Deduping is pretty trivial at this point. I think there's tons of ways to dedupe. It's pretty much a solved problem. But spam content actually is really hard, especially when you look at the social stuff, because these Twitter spam graphs and so on are getting more and more sophisticated, right? They really do create these trust graphs where everything looks legit. The content is engineered to fool good NLP. So it'll hit against all your topic classifiers. It'll seem totally legit. It'll be vetted by all these other kind of network of bots. This problem is getting more and more complicated. The more sophisticated you get, the more sophisticated the adversary gets. This was one of the hardest problems that we had to deal with. So content and interaction features, feature crosses were big here. You got to figure out, like, do I tend to like the same kind of stuff as my friend? And if I have sparse data and I'm just bootstrapping my system, how do I learn those kind of dependencies? So there's a lot of clever ways and hacks for getting at those dependencies. Bootstrapping weight hacks. So like when you first start this kind of ranking system, right, you can't really do learning to rank because you have no interaction data. So how do you sort of bootstrap this with weight hacks in the beginning and try to figure out how to gradually learn it over time? And then we learned scores for all the different interests. I mentioned how we kind of looked at things in this interest-based lens, and we would maintain scores for all the different types of interests. This is basically a story, so I'll just explain how to featurize it really quick. So you have headline features, obviously. Over here you have this byline, which we had like a rich byline because we have a publisher, we have the author that's been extracted, we have times, we have different topics that it's about that I'll talk about in a second. The whole body of the story, all the interaction data, the people that took those interactions, so you have edge weights for all these interactions. And there's sort of it's a pretty rich domain for features, right? Because there's a lot of NLP-driven features and there's a lot of like social interaction features. So I think the main thing to think about in learning to rank versus normal machine learning problems that makes it tricky is that you have this huge corpus of docs that you could show somebody, but then you only show them a certain subset of those docs, and you can only learn from what you show people. You can only learn from this, right? And so it creates a lot of weird biases and creates a lot of problems. In the end of the day, we just ended up using logistic, simple learning to rank approach where you're just reducing inversions. I think somebody mentioned there's been a few presentations on learning to rank here already, so I'm not going to go into detail on that. And then we had a universal feature vector and specific weight vectors for each user. And we snapshotted every session and we trained on the session and tried to maximize the interaction-based engagement in each session. Classification. So, this is a simple thing I think that's worth mentioning. So latent topic models basically don't really work in practice. Nobody ever uses these for anything material unless you're using them to generate features to stick into another model. So if you want to use LDA or something like that for a problem like personalized ranking, the only thing you're going to get out of it is just like potentially interesting features that you can stick into the other learner. But we even found that those were useless compared to all the other features we had. So I'm not a huge fan of these latent topic models because you don't necessarily get additional information out of it, and they're not going to give you labels that are useful to a person, right? Because what matters is, in this case, what are the topics people actually care about and they want to subscribe to? And that's not what LDA or these latent topic models are doing. So if that's the case, then you have this problem of, well, how do I get labeled data to train, a million different classifiers? That's hard, because now am I going to use like Amazon Turk or one of these things? What am I going to do? So distance supervision is the answer. Has anyone heard of distance supervision or weak supervision approaches before? We got one, two, a few. Okay, cool, awesome. It's pretty simple. It's basically, a mechanism to bootstrap training data, a large amount of noisy training data using heuristics and a bunch of clever hacks. And it's used in a lot of state-of-the-art information extraction techniques. What we did, to be precise, is we snarfed a bunch of docs from Twitter. So you take a topic like, let's say, design, right? So I'll build a query on Twitter that's design and some simple expansion of the term design. And I'll hit Twitter with that query. I'll get back all the docs. And then I have different sets of filters to try to filter it to positive and negative examples, right? So I try to take, obviously, very, very high precision examples that I have high confidence in and turn those into positive examples. And then for negative examples, I want ones that are sort of at the margin, right? I don't want random shit that's like about sports. I want stuff that came from that design query that I've now filtered to be sort of a red herring, right? It's like slightly about design, but not really, so it's at the margin. And that's how you get these models to work really well, is largely about kind of really clever tricks to get the negative training examples to be of high quality. The positive ones are easier because you can sort of just go for really high precision by, using a bunch of very precise query terms. Here, we built a lot of closure infrastructure. Like I said, check out plumbing on GitHub. I think it's actually pretty cool. There's a lot of cool stuff on there. We built a full closure backend, closure script front end. We had to build this project called Graph, which is what I described earlier. It's like a way of composing compute graphs. We use that for batch training offline. We use that for configuring production services and having those be well instrumented. And it gave us a lot of wins in terms of debugging things quickly as opposed to, again, just like logging stuff in a normal fashion. We also have a bunch of ML libs. It surprises a lot of people, I think, how fast we could code things on a machine learning, in a machine learning sense. Like we basically had used a lot of macros and arrays and so on to get very, very high performance out of Java and Clojure on top of Java. And I think that was something that a lot of people were skeptical about because it's a dynamic language and so on, right? But we actually got really, really fast stuff, so you can check that. I think there's a project called, I forget the name of it, but it's basically all about Clojure macros on top of arrays. Pain points. So one of them is presentation bias. So people click what they're shown. So you have this explore exploit problem where a new doc comes in, you want to explore it, you show it to someone, they click on it, and then now it gets all these upweights, right? And then other people are more likely to see it, and you have this whole problem of now people just keep getting shown the same shit, which is in that inner circle of what I showed earlier, right? So it biases this kind of viral feedback loop. This is actually a super hard problem. I think a lot of people don't realize how much, when you complain about Facebook and their like crappy viral content that you get in your newsfeed, I think it's less because they're trying to engineer for that, and it's more because it's genuinely really hard to get rid of that issue. Data issues, again, like the spam bot problem was huge. That just reinforces that issue I mentioned because they intentionally kind of engineer these botnets to make it look like something has a massive amount of social validation. And then they generate high quality text, so it's going to fool all the NLP. So it fools your NLP, it fools all your social weights. You get this stuff pushed up to the top, and it's really hard to get rid of it because then you have that reinforcement bias I just mentioned. So that's a huge problem. And then bootstrapping distant supervision is hard, but it's actually an okay problem. We found that to be less tricky. Bootstrapping ranking, on the other hand, is super hard because you have really sparse interaction data in the beginning. So you have to start with these weights that you kind of hand tune, and then that biases your training data, obviously, and there's just like so many problems with that. So bootstrapping a learning to rank approach from like a hand-tuned weights and IR type approach is a super tricky beast. There was also this problem of social versus interest-based personalization. There's tons of arguments about the team, or within the team, I mean. Some people prefer stuff that's very, very like personalized to their interests. Some people prefer stuff that has more friends that have interacted with it. Everyone has their own preferences. Even the researchers bias things based on their own preferences. So, one person will try a set of features and claim that it doesn't work because they don't like that type of content, and then other people will try the same set of features and it works. So it's quite interesting. This was a huge debate. Lesson learned. So I think we went a little overboard with the Clojure not invented here type stuff on this startup. Like we built a lot of stuff which is really cool, but we also missed the boat on some really important open source that we should have been using, like Spark, for example, and things like this that could have made it much easier for us to distribute all of our training. I think it was really cool learning about this whole fully automated classifier pipeline that we built. So we had this distant supervision approach that I mentioned wired up to just constantly automatically retrain. So that was cool because you want topics that are being discovered over time. So our set of topics would grow over time organically, and then we periodically retrain all the classifiers so that they're up to date on recent content. And I thought that was pretty cool that can happen in a completely automated fashion. So that was one of the coolest and most surprising things to me about that startup from a machine learning perspective. And then it was also neat to see how much we could optimize interactions. When we had this big sprint in a couple months to really try to get interactions up, and we increased them by 50% just by kind of trying all kinds of different features, and that was pretty awesome as well. Last, I learned that when data is too sparse, it might not be a good idea even to try learning to rank and fancier models. I think one thing when it comes to building machine learning products that we took away from this is that you probably should, meter the sophistication of your approach based on how much traction your thing gets, which then is what generates the data that you're training on, right? So if your product doesn't have much traction and you don't have much data to train on, then it's probably not a great idea to spend a shitload of time doing this sophisticated learning to rank approach. So candidly, I think we kind of rat-holed on that too early, spent too much time, and the product itself was kind of borked, and I don't think people cared about it that much. Cool. So those are the first two startups I did. So I'm going to talk a little bit about what I'm doing this year. and the 2 new startups and some open problems in those. So CAI is the Central European AI Institute that we've created here. It's operating out of Prague and Bratislava. Our goal is to start 10 companies in 3 years and invest a total of $65 million. And we've so far done 2 companies this year and invested a total of 1. We started 6 months ago. We do unsexy low beta stuff. Beta is a term from finance. It basically just means uncorrelated with the market. I'm using it in an abstract sense here. So we're not doing any food delivery startups or any of that kind of shit. If there's 20 of it, we're probably not doing it, right? We're doing stuff that's pretty uninteresting to the masses, which is what we like. We don't like to compete against other really smart people. That's a bad idea. Okay. Proprietary models built on proprietary data. I think that's the core thing that gives a machine learning startup defensibility, right? Like, let's say that you come up with something super interesting and you start making a bunch of money, but the data is just publicly accessible, right? And you go around and you're like, well, we have the smartest team and the best models, and we have this new, slightly tweaked, deep learning model. It really doesn't matter, right? Because somebody else is just as smart, and they're going to come and compete with you, and you're going to have your margins eroded over time. And so really what you want is this advantage where you get a compounding effect of proprietary data and proprietary models working together. Google is like the canonical example of this, right? Over time, they have so much more interaction data than anyone else, so all of the problems that they want to solve, from ranking to machine translation to anything else, they have this massive advantage, and it's very hard to compete with them. Also, they get better and better and better at delivering low latency results all around the world. And so you want this kind of ability to compound this proprietary advantage. You really don't want something that's easy to start. So it's kind of a complicated process to figure out, I think, what are interesting AI problems to focus on as a startup. And again, you want to avoid this at all costs. I think this is the killer of so many startups. I mean, we've done now with Data Collective, so many AI startups going back to 2010. And since I've been doing this stuff since the mid-2000s in Silicon Valley and had so many friends starting these companies, this is the #1 killer of this type of company. As people start geeking out on the tech, they spend multiple years on the tech, oftentimes 18 to 24 months without launching, and then they just die because nobody cared, right? So really spend a lot of time to think about your problem and set your problem up and try to invest in something that people are going to care about, because ultimately you're going to have to go heads down on some of these hard R&D problems that will take 6 to 12 months to solve. And you'd really rather do that once it's already validated that that's a good idea to invest that time. So I'm not going to go through this whole thing, but this is just a little bit of a slide about our process that we use for incubating these startups. The part that I want to focus on is this. This is addressing this hammer seeking a nail problem. So we do this Q0 thing before we even invest the first $500,000 and we make a go, no go decision. We basically take a ton of time, 3 entire months, just to explore the market. This is like market research, talking to customers, etc. We're looking for these factors. We're looking for the total addressable market, meaning not like some outlandish view of like what if we had 1% of China and this kind of crap, but like how much of the market can you actually capture, right? If there's competitors there already, what's a realistic new slice of the market based on what your idea is and your entry point is? What are the catalysts there? How are people losing their jobs because of this? Are people losing potential revenue opportunities because of this? Is it killing an industry? You want some major catalysts. Otherwise, it's going to be really an uphill battle for you. Market entry strategy is there, and that goes together with this Trojan horse idea. Is there a way that you can wedge in through a small, like sneaky, narrow niche that other people might not see, but it opens you up into this massive business opportunity? Because if you just directly try to attack the massive business opportunity, it's like having 3 dudes in a ladder and trying to lay siege to Rome, right? It's a bad idea. Defensibility, I already talked about. That's this compounding models on top of data thing. And I basically think that's the one true item of defensibility that you want to think about with any machine learning startup. If I look at a startup that wants to pitch me for an investment, and it doesn't have that defensibility aspect, it's like an auto pass. I just don't even spend any time on it at all. Okay, now on to the cool stuff that we're doing now. So Tower Street is a cyber MGA. That's like a cyber insurance company, basically. An MGA means a managing general agent. This means we actually underwrite the risk ourselves. We don't sell analytics tech to insurance companies. We are an insurance company. I'm not going to go into all the details of what an MGA is. It's a bunch of finance nerdery, and you guys are computer science nerds, not finance nerds. So, unless is there anyone else in here that's a dual nerd like me? No? I didn't think so. So that's why I said I was going to leave that one out. So indirect losses are what we're focusing on, right? So right now you can get a policy that will cover you on direct losses. Like somebody steals your data, they go and sell it on dark web, and basically you have to go pay your customers, pay a law firm, pay some consulting firm to come in and do forensics and all that. You can get an insurance policy that will cover that up to about $200 million because people are not confident in their models. So they're only willing to insure you that much. What we're doing is we're going after these indirect losses that are very hard to measure, right? So you sustain some brand damage. What's it do to your stock price? What's it do to your credit rating? And how does that increase your borrowing costs? And then what does it do to your top line sales? This is what the cyber insurance market looks like up and to the right. It's grown at about 35% annually. It should be $50 billion in 10 years. Right now, this is pretty small. Just to give you a sense, like property and casualty insurance globally is like a $1.5 trillion market. It's huge. So this is actually a very small slice relative to where it should be. If you think about the value of the world's digital assets relative to the value of the world's physical assets, it doesn't make sense that they're so far off, right? So I think the reason they're so far off is because it's so hard to quantify the impact of these breaches. So the catalysts here are SEC and EU regs. Now the public companies have to actually disclose these. It's mandatory to disclose them. There's been a ton of high-profile breaches and these large indirect losses. You know, like the Target breach, it's estimated that they lost several $billion when you add it all together, including these these indirect losses, rather. The CEO was fired. Sony CEO ousted. More and more, I think you're just going to see this issue where CEOs get fired, boards members get fired, CIOs and CISOs get fired. It's becoming a disaster when people are taking these large breaches as a public company. This is a quick view of like the dashboard that we sell to the CFO. The important thing to focus on is just here, right? It's like we're showing them relative to their peers what their prospective loss is on these different vectors that people are not really currently trying to quantify at all. So this is what I was talking about earlier when it comes to the difficulty of casting the research problem correctly. So when we first looked at this, we tried to baseline it against some papers that we had read from what other companies are doing that try to quantify cyber risk. We saw them set it up as a supervised learning problem. There's publicly available breach data sets. And what they would do is they'd go to these breach data sets, take the recorded breaches as positive examples, and then take a random sample of companies that weren't attacked and treat those as negative examples. Right, and then they would use these security features from publicly available data like census that talk about, you know, what's your DNS records and all this kind of stuff, right? And this was a fail. It's actually set up completely incorrectly because breach companies don't have worse security, and the background companies that haven't been attacked or haven't reported attack don't necessarily have better security, right? It's actually counterintuitive, but it's probably the other way around because the people that haven't reported breaches have also been breached, but they just don't know. So they're even dumber, right, than the ones that were breached. So in fact, the whole thing is just set up totally incorrectly. And I think this is a good example where, in fact, all the other startups we've looked at that do cyber risk have set the problem up like that. And we figured that out reasonably quickly and stopped pursuing that path. I think it's a great example of how setting up the research problem is just as important. Another approach we could have taken is just keep doing fancier models with this totally fallacious approach. So how do you estimate the likelihood of a breach? It's a huge problem because you don't have good historical data. You can build rich current data, you can scan, you can grab all kinds of different data, but you don't have it historically, so you can't really learn off of it. Also, even if you did have it historically, it's not necessarily going to have good predictive power as you go back over time because it's a dynamic environment where the adversary is constantly trying to change and evolve. So if I look at old data, maybe it doesn't even help me anymore. So we've asked this question, could we find some static indicators maybe that are a better and more robust and more stable predictor of risk? These are all open problems. A lot of what I'm going to talk about in Tower Street and Raptor are super interesting open research problems that we're focusing on now. We've also looked at the relationship with catastrophes. There's a long and rich history of trying to quantify earthquake, hurricane, and so on types of risk. These are cases where the events are sparse, they're correlated, There's a lot of interesting statistical artifacts, so we've wondered, hey, maybe we can draw from this. It's quite similar in a lot of ways to cyber. But then once you look at it, actually there are some stark differences. So one is that in catastrophe risk, right, the impact doesn't really change in type, right? It's hurricanes you're looking at every time. It's earthquakes you're looking at every time. They might change in magnitude, but it's still an earthquake. And basically, you can use physical models to do these simulations, right? It's like just basic stochastic models. There's the laws of physics and so on that we have. But in cyber, it's not the case. You have incentives of these cyber attackers, which change over time. Some people are out to get somebody. Some people are just out to steal data so they can sell it on dark web. There's tons of different motivations. And the impacts over time change, right? As you get into IoT stuff, people can hack into a system and screw up something in the physical world by coming in via a digital channel. These kind of impacts are very different than things you would originally model if you're thinking of and looking at data from 10 years ago. So that makes it pretty challenging. So what we end up doing is looking at these different factors over here on the left-hand side. The industry baseline, their infrastructure security, social engineering means things like email phishing and so on. And we try to basically get as best as we can some kind of proxy for these different factors over time. And we look at the frequency of breaches, the size of the loss, and uncertainty load, which I'll explain here on this next slide. So the way that you price specialty risk, this is called a specialty risk, is you have these different load factors, they're called. And a lot of these things, like all this stuff here, all this stuff here, these are all finance things that you can kind of proxy by looking at other areas of insurance. The important things to focus on are the uncertainty load. That means how uncertain am I of my ability to quantify this risk? The expected loss frequency. How often every year do I think somebody's going to sustain a breach and a loss? And the severity, as we'll see, actually there's a hack so that you don't have to try to quantify that. There's the simplifying assumption. So you can start by rolling out, because nobody else quantifies this risk yet, we can just give people really low losses. And so it'll hit the limit every time. Right? If I say I'm only going to insure you up to 20 million bucks worth of stock price loss, you're going to take the policy because it's going to become a best practice, because otherwise you have no policy, you have no attempt to quantify the risk at all. So if I'm a board of a bank and I have this choice, it's literally my fiduciary duty to go and take the choice. And they're going to kind of deal with whatever we give them in terms of a limit. And so we can just assume that it's always going to hit the limit because we're giving them a low limit, which is awesome, right? Then we don't have to try to quantify the magnitude right away. We can incrementally scale up our limits over time. So now it reduces to just like this likelihood and uncertainty. And basically, you know, we can get confidence, some kind of a confidence metric based on the sample of data that we have. How many breaches do we have? What do we think about the quality of this data? We can come up with some statistical confidence score. And we can estimate the likelihood from the risk features that we have available joined up with the breach data. As I mentioned earlier, these indirect losses, quantifying these is really hard. This is a very open problem for us. This is basically a financial engineering, merged with machine learning problem. Because you have to normalize out these market and industry effects. You have to normalize out news or corporate events like earning announcements and so on. There's a lot of these factors that could also be causing this stock price decline or credit rating change or sales decline. And so how do you know what's causal? You have to, as much as possible, get towards a notion of a statistically significant loss that's been caused by this breach. And then once you do get to that notion of a statistically significant loss, you have to somehow define it as such in the policy. Right, in the actual insurance policy, so that you can make it as parametric as possible. You don't go into legal battles. You basically have it all wired up so that when something happens, everybody's agreed upon the data, and you can just pay out because you've defined it clearly and parametrically. We've been starting to build some investigation tools so you can think. I just showed this slide because I think it's smart when people do this. Like in general, when you're looking at a new machine learning problem, you want to kind of inspect the data and mess around with the data and try to understand the data. Build little charts and other kinds of tools and tables and so on to help you understand that. I think that's super important. Because again, sometimes you may not even be able to learn from the data that you have. And if you can figure that out by looking at the data and then doing some early experiments and then sort of trying to go back to the data and realize you have a data problem before you start focusing a lot on different models, I think that's really smart and it avoids a lot of rat holing. This is kind of what our roadmap looks like. You can see that in the beginning. It's very simple. kind of like industry-based frequency, right? Like kind of static measures, like industry is obviously a static factor. And then this is sort of I like to think about horizontal layer cakes when you're building models, right? It's like, give me an end-to-end skeleton of the system, even though each individual piece might be naive. And then over time, I want each piece to become richer and richer. You don't want to do a depth-first search on like one of these areas, because it's going to be months before you have anything useful for each area. And then later on, you're kind of, again, you've done the hammer looking for a nail thing. You've spent 2 years on R&D, and the whole thing might be screwed once you actually try to show it to someone. You might be totally off the mark in terms of the problem you're solving. So this is sort of like, I think, a good example of building out a roadmap where you're doing a breadth-first search and then building out richness layer by layer. Okay, accumulation risk is interesting. Breaches can obviously be correlated. Someone comes up with a new exploit and they attack many people at the same time. So you got to make sure you don't take on too much risk. Cyber is also becoming, interestingly, probably the #1 risk that all of auto insurers are worried about, because of the future of autonomous vehicles. The cyber risk to automobiles becomes really huge. Supply chain, because of IoT, there's a lot of opportunities to attack different parts of the supply chain and cause disruption there. And physical damage, there's already been some examples of this, like figuring out to, destroy take down an HVAC system or take down some kind of digital system. Like imagine if somebody figured out how to attack a hospital and turn off the power, stuff like that. It can get pretty nasty. So that's Tower Street. Lots of really interesting open problems. More open problems than solved ones there. Raptor. Raptor is Bloomberg for back office. Do you guys know what Bloomberg is? Or no? Yeah, everyone knows the Bloomberg terminal? Okay. So this is the same kind of idea. It's a terminal per role, but for people in the back office that are working on the bank risk, not people in the front office that are working with market data and trying to make money. So these guys are trying to reduce risk instead of make money. The market here is pretty huge. Banks spend about $100 billion on this every year. $20 billion alone just on analytics software for this stuff. And it's growing at 20% annually. So this is a pretty big deal, getting again to I'm putting these slides up here even though this is like a technical audience, because I really want to reinforce for you guys the importance of doing the analysis up front on these problems and not just diving into something you think is interesting. A thing that's growing at 20% annually and already $100 billion is awesome. That's what you want, right? Catalysts are also what you want. Like, look, this is an awesome chart right here, right? Look at 2011. It's like, great. This is what I want. So basically, 9/11 happened. The world became really concerned about terrorism financing, and they started to regulate the banks a lot more. 2008 happened, which is obviously the financial crisis in the U.S. with the mortgage-backed securities and all that, and that sent ripples around the world. And then that yielded another wave of regulations. And by the time 2011 came around, they started to really enforce these things hardcore. And there was this 20x explosion in fines. Today, in 2016, the fines globally against banks for money laundering and sanctions violations are larger than fraud in the banking system. So there's more fines than there is fraud in the banking system. And the reason why is actually pretty simple. The reason why is that we use statistical models for fraud. We have for many years, just like we do for spam or security. But in this domain, it's still all these weird old rules-based systems. And so they're much more easy to exploit. And so the activity going on in money laundering is sort of not super hindered by the naive rules-based systems that people are using now. And like for Tower Street, this is a catalyst you'll see that I like, CEOs are getting fired. It's like great way to motivate people to make decisions is when they're scared of losing their job. So Deutsche Bank CEO quit recently. You'll see the Wells Fargo disaster. I'm sure you guys have seen some information about that. Has anyone seen that? I don't know how much that's leaked outside the US. Yeah, it's a huge problem. Basically, they got caught, opening tons of extra accounts for people that they didn't want to open and trying to get them hit with additional fees so that the reps that were opening these accounts would meet their sales quotas. So huge disaster. They didn't catch it. And then the financial regulators in the U.S. came in and caught them, and they're just killing them right now. So that's basically the deal. It's a pretty big problem in global banks. This is a sort of a quick summary of what it looks like with Raptor. It's just basically take all the data that an analyst needs to use to make a decision. For example, onboarding a new customer or deciding whether or not a transaction is risky and looks like it's part of money laundering. Take all that data, stick it into one screen, use machine learning to rank it, highlight the risk, and basically dramatically cut down the analyst's time to accomplish their task, and also dramatically cut down the risk by kind of trying to surface the needles in a haystack up to the analyst. So there's many different kind of classes of problems here that are cool. Computer vision is one. Basically, this is just a quick slide from the CMU library that we use. You kind of have image distance for ID check. You have detecting faces out of the story, right, or out of the ID rather, and then maybe somebody takes a picture with their mobile. Maybe I have another picture of this person, and I want to see, do I believe this is all the same person, right? Another problem is maybe I want to look up this person in a giant database of bad actors, right? So there's all these watch lists of terrorists and so on. You know, there's this one in the US called OFAC. There's one in the UK called Her Majesty's Treasury List. There's all these different lists. And right now, it's all text-based screening. So I'll take a person's name and I'll screen it against this list. But obviously, if I'm a terrorist and I'm coming to sign up for a bank account, what do you think the chances are I'm going to use my own name when I'm on a publicly available list? I'll let you take a guess at the likelihood. Right, so, but it's probably harder to fake a face. So, you know, we're interested in looking at some of these techniques also for images. For NLP, the big thing is detecting adverse news. So, you know, the problem with the IR approach that's really easy to do, just drop it into an index and use that, is that you get high precision, or you get high recall but low precision, right? You get tons of false positives like these ones here, right? So we look for John Smith. In this case, you know, poor John Smith is actually the good guy. You know, first he's a judge, and then he gets killed. But the poor John Smith is getting, you know, these are popping up for him when he's trying to open up a bank account today. So, and then poor analyst who has to weed through all this crap, right? And try to imagine if you're looking at hundreds of stories like this for a common name, how difficult it must be to try to find if something's actually going on. So enter NLP instead of IR, right? So here, the simplest thing to do is some sort of a sentiment type of classifier. You know, like, is this adverse news or not, right? So you use a keyword-based approach, and then you filter it based on this kind of sentiment classifier, right? That's the simplest way to go. The next way to go is sort of this problem of relation extraction, which is a super interesting problem in IR and where a lot of people have focused a lot of this distance supervision energy. Here again, it's about generating noisy training data. In this case, this is a little bit more precise than what we did with Prismatic because it's more recent. So you want to look for mentions of people in the stories together with bad news. And it's, again, pretty easy to create positive examples because you can just create more and more precise filters, so you can always get high precision on the positive examples. Negative examples are trickier because, again, you want these ones that are like on the margin, right? That's how you're going to train a really good classifier that gets good results. And so you want to do things like finding a list of judges and searching for their mentions, right? And then you know that you have guys that have sentenced somebody instead of done a bad action. Right, so you want to do a lot of these kinds of hacks. It's actually, this is a good example, I think, of how to really do good machine learning in practice. You really have to know what you're doing. You can't just loop over a bunch of Python libraries and try different models, right? Because in this case, you have to understand, what am I trying to learn? What do I need out of my training data? How am I going to hack my training data so that I have these negative examples that will help the classifier actually learn what I want it to learn? Because you can also just go and take a whole bunch of shit that you know is not about bad news. It's actually not going to be helpful at all, right? So it's I think, a great example of how important it is to actually know what you're doing and be able to think about the theory when you're applying this stuff. The heuristics tend to fall into three categories. Like, either it doesn't work, you try an idea and it just doesn't work at all. It has low coverage. Maybe you have 100 training examples that you're trying to get and only 3 of them are impacted by this change. And the good ones tend to have a really big impact on performance, especially when you're looking at, again, generating negative examples. You kind of have these eureka moments where you try something and it really works and you're like, holy crap, this is like magic. And that's how it is, I think, when you're doing these weak supervision approaches. Also, different sources have different rates of true versus false positives. You know, obviously, if you look at news versus if you look at court proceedings or other corpora, you're going to see very different results. So it's important to think about that kind of stuff. You have basically the ability to even use previous versions of your classifier that didn't work well as heuristics. There's just a lot of combinations of things that you need to try to basically generate good negative examples. And again, I think like that's the sort of whole game with the weak supervision approaches. How do you cleverly generate good negative examples that are at the margin? Another thing that's a twist for us is we have to do this across all languages, more or less, that matter, right? Which means that we don't get to use things like, there's a Stanford dependency parser and it only works on English, and we can't really use it. So that's a great source of features. If you read a lot of distance supervision papers, they make use of those features. In my last company, Prismatic, when we did an experiment on this for detecting company events, we used those features, and they were very powerful features. We can't use any of them because we needed to work on Chinese, Arabic, everything else, and there's no dependency parsers for those. So that makes it also harder. Let's see, this is the interesting thing about the models. Again, like we're trying both deep learning and logistic, and basically over time, they're kind of converging in performance. Initially, the deep learning stuff worked way, way better, and then as Vlado, the guy who's working on this NLP stuff, has been featurizing better and better, I think the performance is starting to converge a bit. So I think it's like a really interesting, noteworthy thing that in general, again, there's many ways to capture the dependencies, and in the end of the day, sometimes it kind of becomes a wash over time as you try a bunch and learn about how to featurize it. For some problems, like especially ones in computer vision and some in speech, the neural net stuff is really just keeps on giving state-of-the-art results, and it's hard to beat it or approach the results with like just using logistic. But for other domains, like these kind of problems, it's not clear-cut yet. So this is just, looking at a recurrent neural net, and I'm just going to go through these really quick just to show you a couple of interesting, noteworthy things. So the interesting thing here is the word embeddings, right? Using pre-trained word embeddings is really cool. In general, I think all the transfer learning stuff going on recently is really, really cool stuff to research. But it helps give better performance. You're leveraging this lack of training data. You're able to do stuff across multiple languages, across multiple tasks. So that's been something that's pretty awesome. And then in convolutional nets, we're trying these too. What we've found, which is interesting, so these are coming into NLP a lot lately from imagery. But what's interesting, I think, is that more or less here, we're also getting similar performance. So right now, it's pretty much a tie, right? So I think in general, it's quite interesting how even for this problem where we would have thought in the beginning that these neural nets were going to exploit some structure that maybe the other models aren't, we still get to a tie over time as we get better and better at engineering the features. Open problems with false negatives. This is sort of like more hardcore NLP issues, right? Issues spanning multiple languages. Your co-ref resolution is a big one. Lots of different problems in discourse analysis overall. And then formatted text. Because you look at like court proceedings and things like this, you have actual formatted text versus just a straight up news article. You got to figure out how you're going to deal with that and parse that stuff and featurize it differently. So normally what you do for that is you actually have to build classifiers for different document types, and then you whack those with different feature extractors. So key takeaways here. Improving the training data helps more than tweaking the model. Again, you can keep trying tons of different neural net architectures, and I think this is like, this is a slide from Vlado, this academic trap, because I think in academia they do this a lot. It's exciting to try these different models and try to get like a tiny performance boost, but in practice oftentimes, you don't have this canned canonical data set to use, and the bigger problem is like getting better data, so you're really usually better off to just spend more time trying to find better data and trying to engineer better features out of the data. Understand where your data is sparse and where you can improve it so that you can predict better in that part of the input space. I think that kind of stuff's way more important in general than tweaking and playing with different models. Risk ranking and risk networks is the next one. So we think about like this whole Google for risk idea, right? I mentioned earlier that Google wins on ranking because they have all this interaction data. And we win on risk because we have this analyst annotation data. So the interface I put up earlier is the one the analyst actually interacts with. They click on stuff and say, yes, this is high risk. No, this was a false positive. I'm going to reject this account. All those interactions are the same kind of interactions that Google uses for search ranking or Facebook uses for newsfeed ranking. And so that is a super rich source of data that we capture, and no one else in the world, in their products or within banks, is capturing that data. So that's a huge advantage for us. Basically, the goal of this ranking problem is pretty simple. You're searching for, all these negative news sources and other corpora, and you're trying to find high-risk items and surface them to the analyst. You don't want to miss anything important, and you want to avoid a large number of false positives, which makes it harder for them to find stuff that's important. So there's a number of problems. There's accurately identifying the name of the person. There's identifying the context that the person is mentioned in, again, so you don't get spammed with tons of mentions. And of course, this is a bigger issue. The higher the likelihood is that a given piece of content contains a certain name. So for common names, this is a huge issue. And then you need interpretable results on all levels, because this is in the risk domain within banks. Everything is regulated. So you can't use like a deep net here or something where you don't even know what the hell's going on, because you can't explain that to a regulator. They're like, what's going on here? What are the parameters? How does this work? And you're like, I don't know, right? It doesn't work. So you got to use simpler stuff that you can actually explain. And then you have this analyst feedback, implicit versus implicit, right? Again, just like with Facebook or Google or whatever, you can look at dwell times, you can look at click data and so on, and you can of course look at explicit signals like, canceling out a story and saying that this was a false positive or rejecting an account. This is just an example of this whole like interpretability thing. So this is like what a management dashboard looks like in Raptor, and you can see that we have the actual parameter values here for them to see. And you can print this out and show it to a regulator during examination, so it's super clear what all the model parameters are and their values are. And then they can tweak these, because they might say like, no, this is too risky. Even though the learner says this is optimal, I want to crank it up and say that anything that's below a 95% face match, I have to make somebody look at that. So this is an example of how, like, in practice, you have all these constraints on what you're doing based on the domain you're playing in. You can't just simply do whatever is optimal from a machine learning standpoint. Prediction versus ranking is interesting here. In prediction, you want scores. You want to filter. Ranking is still kind of interesting. And the loss is basically your error rate. You're really trying to predict, and you really care about that score. In ranking, it's different. You don't really care about the score. You really care about optimal ordering of results. And the loss is the number of inversions, like I mentioned earlier, this whole learning to rank problem, right? So it's pretty different setups for the same kind of problem. Again, like we talked about earlier, it's super important to understand how to cast the problem. So, which way would you cast the problem is an interesting question, And probably you kind of need to do both for different parts of the problem, right? So maybe you want to do learning to rank, but then you also want to filter, and you also want to show some score, so you need to both predict and rank. Risk networks, this is really cool, right? This is this problem of you have a social network with a bunch of people, the companies that they're connected to and their beneficial owners in, and you want to evaluate that risk at all different levels. There's node risk, there's edge risk, there's risk through certain paths, there's risk in certain subgraphs, and you basically want to understand where's the risk in this big commercial graph, right? So this is the Facebook for risk thing. So you have links between all people and companies. You have this like page rank kind of notion, some sort of way of quantifying the network risk. And you want to see the riskiest pass through the network. If I'm doing diligence on a person, I want to know, are they connected to somebody who's like in the Panama Papers or something like this? And then if there is that connection, I want to drill down and evaluate these connections and see if I should open a bank account for this person or not. So the first thing you got to do is build this multigraph, right? You have multiple relations between each node, and these relationships can be personal ones or business ones, and there's different structured data sources that you can mine to start building the graph. Wikipedia, there's company registers around the world in different states and countries, there's Panama Papers and so on, which also have extracted structures relationships, and you need to deduplicate all these nodes and merge it into one big multigraph, and that's the start of bootstrapping the graph. Here's an example from David Cameron. So there's some speculation that maybe he stepped down because of his dad being implicated in the whole Panama Papers thing. So he was connected to something there. It created a lot of drama. And so this is a great example of like why you want to look at graph analysis for evaluating risk financially. The second thing you want to do for building this multigraph, this is a later stage that we'll tackle, is once you get all the structured data together, you can mine a ton of data out of unstructured text, right? So different kinds of news articles, different types of corpora that might be put out by the government. And if you can do relation extraction like we're doing for the negative news classification, there's a lot you can do here. Cool. So the roadmap for this is basically start with these risk scores at the node level. CDD and EDD, by the way, I should have explained this, is customer due diligence and enhanced due diligence. So this is like, screening people against watch list and other structured corpora of bad guys, and then screening people against big unstructured corpora like news sources and leaks databases and so on. And so if I take your name and I screen it against all this stuff, I get this big set of documents, these hits against your name. I can use those to bootstrap a risk score, and that's basically the score at your node, right? The initialization score. And then if I take that same approach across companies and I treat a company as just the sum of its beneficial owners, now I can bootstrap the entire graph with an initialization score, and then I can use a whole bunch of different network analysis approaches to create a better score over time using these iterative algorithms, right? And then I can do subgraph risk ranking, so I can try to identify really risky cliques within this graph, which is also quite neat because then you can start to look at things like, for example, we were just with a big Swiss bank this week, and the Bahamas papers are about to come out as well, right? And they're concerned about what's going on with my customer base once these Bahamas papers comes out, right? And so this is a great example for doing graph analysis, and because you don't want to just tell them like, oh, there's a hit for this person, there's a hit for this person, there's a hit for this person. Ideally, you can give them a richer notion of sort of a mega case, right? So like, here's a big network of companies and people that are connected, and now we know some new information about them. You need to take a team of 10 as like a SWAT team and go put them on investigating this. This is a big issue, right? Versus just naively throwing up individual alerts. So this is the kind of stuff you can do when you do this well. It's super exciting, and banks are very, very excited about it. Link prediction is another one that we'll be able to get to hopefully later. Trying to infer new relationships, especially based on behavioral data. If you have all the transactions and other kinds of behaviors that people are engaging in with one another, both as individuals and between individuals and entities, then there's tons of different techniques that you can use to try to create new edges and predict new edges in the graph. And in the end of the day, you can then sort of take, again, like a distance supervision and sort of bootstrapping a learning to rank type problem so that you can get even more sophisticated way of scoring the graph for risk. And then ultimately try to identify sort of patterns in the graph that are highest risk, whether it be an individual, sort of a path through the graph or a subgraph. Last bit that I'm going to go through, so I'm almost done here, just like 5 more minutes, is the new topics that we're looking at. So as you can see so far, the 2 companies I showed are in the computational finance space, right? We're trying to quantify risks that are very, very difficult to quantify because it's a relatively unsexy problem, but there's a lot of money in it. And again, like earlier, that's the kind of stuff we like. Computer vision is another awesome one. There's many catalysts here, both business-wise and technical-wise. So problems like automatic diagnosis from medical imaging. There's a lot of really cool stuff using aerial imagery from space or from Cessnas, like the Space No guys are doing here in Prague. And then computational bio and medicine are very interesting. We have several companies that we've invested in actually from DCVC that are incredibly successful with things like drug discovery or generating industrial chemicals in a more efficient, economic, and more eco-friendly way. So this is another huge area. These are all areas where there's a massive amount of data, so it's kind of tricky. It's like big data and machine learning problems. They're usually kind of unsexy, old school industries where there hasn't been a lot of innovation before. Like one of my friend's companies that uses computer vision uses a company called Planet Labs' data. Planet Labs is one of the first satellite companies that will get to a weekly and then daily cadence of the whole Earth. So they'll have a snapshot of the whole Earth every day. And so they use their data to predict agricultural yields, right? There hasn't been people applying this kind of tech to predicting corn yields for a long time. And same is true for many applications in defense or many applications in financial prediction. And so there's a ton of interesting problems there. And actually in computational bio, like when you hear about biotech, because the word tech is in it, you oftentimes think it's technically sophisticated, but it's not true. I'm not sure why they called it biotech, because there's no tech. It's actually science, right? But it's like people in lab coats going into the lab and messing around with test tubes. It's not like hardcore computer science. It's starting to get there now, but you would be very, very surprised if you dig into how the drug discovery and development process works versus how you would think it should work as an AI person. You're going to see a ton of opportunities. These proactive full stack MGAs, these are problems like Tower Street for other kinds of risks. So this is climate change. Climate change is obviously a huge risk that affects tons and tons of different things. And this is probably one of the next couple of risks that we'll look at after cyber. It's very, very hard to quantify. The data is very sparse, very long term, and it's pretty gnarly. And in fact, I didn't tackle it first because it's even worse problem than cyber in terms of difficulty. Supply chain is the next one I think we'll probably go after. Huge problem, tons of data, increasing number of sensors, and massive, massive value is lost when there's disruption to some core supply chain. This is what I was just talking about actually, Descartes Labs. That's my friend's company that deals with all these different prediction problems. They're quite cool. They've been doing really huge deals lately. And I think they're going to expand out beyond just doing agricultural prediction really soon. This I just showed to just like give you a sense. This is Planet Labs data of like, this is the flooding that came up in September. And I just wanted you to kind of imagine, based on looking at the change in this image from the GIF, like how interesting it is to featureize that image, right, and be able to make predictions off of it. It's pretty obvious how many different ways you can featureize the changes in this image and make interesting predictions. Atomwise is a company we have that does deep learning for drug discovery. We have several companies that do this. The tendency for them is to discover new molecules that are really interesting and be able to predict what's going to happen to them in clinical trial, and then just flip those to the big pharma companies. Because running clinicals and doing production and everything is kind of a giant pain in the butt. They're able to sell the IP for these new molecules to drug companies for very large amounts of money. So we have multiple companies that are doing that. That's an exciting area that I would encourage you to take a look at. This is the lab of another company that we have called Zymergen. They manufacture industrial chemicals for all kinds of different products that are used, like very, very large scale products, the kind of stuff that Johnson & Johnson and companies like that do. So it's basically AI plus robots running this lab and just manufacturing chemicals. And this is the thing we're doing, the CAI thing again. This is like the kind of problems that we look at. This is our evil base. And this is the inside of our evil base. So that's it. I'm done. Okay. Thanks, everyone.